Okay, good afternoon, everyone. Thanks for coming to today's seminar. It's a brown bag research seminar today. The title of the talk today is Illinois Groundwater Source Resource Geothermal Resources. My name is Nancy Holm. I'm the seminar organizer. We're very pleased to have the three researchers who worked on this project with us today. Dr. Dave Larson, who's been for 22 years with the ISGS, Xinli Liu from ISTC, who's been here for 3 years, and Dr. Thomas Holm, who's been at the Water Survey for 28 years. This was a project that was sponsored by our Hazardous Waste Research Fund, where we provide funds for seed grants to different researchers here at the U of I and elsewhere in the state for their projects. So today, Dave, Xinli, and Tom will alternate speaking about their project on the groundwater source geothermal resources. Tom Holm will begin. Thanks very much.
Thanks, Nancy. We'll do this tag team style. I'll give a few brief remarks, and then Dave will take over. Do the acknowledgements first so I don't forget about them. Wonky Ewan gave us lots of good help. First, he helped me with the geochemical database, and then Xinli with his thermal modeling. This project, as Nancy mentioned, was supported by ISTC, and I really should give an acknowledgement to Todd Rusk. This was Todd's idea at the beginning before he went on to bigger and better things. I hope we've made it a good product. You'll tell me at the end, right? Ground source geothermal heat pumps take advantage of the temperature difference between the ground at not too great a depth and the surface. This graph is for Ottawa, Ontario, and shows soil temperatures at 3 different depths, about 1 foot, 2 and 5 meters. As one would expect, the shallowest one has the widest swing in temperature. About 20 degrees between winter and summer. It's damped out quite a bit at 2 meters, and at 5 meters there's hardly any change at all. In the winter, we can take advantage of this delta T by extracting heat from the ground and using it for spaced heating. Similarly, in the summer, dump heat into the ground and use it for cooling. Xinli will have more to say about this in his part. Here are groundwater temperatures in 2 parts of Illinois. Dave will show you a map where these are. There are 2 study areas. Mason County is right in smack in the center of the state along the Illinois River. The median temperature, the median groundwater temperature is about the average air temperature, 14 degrees. American Bottoms, which is East St. Louis in that area, the temperature's a little higher. That's not too surprising. That's a little farther south. There are 2 kinds of ground source heat pump systems, either closed loop or not closed loop. The closed loop conducts a heat transfer fluid, basically antifreeze, through the ground and into the heat pump in the residence. It can be either horizontal, buried a few feet below the ground surface, or vertical in a well constructed for just for heating and cooling. The other kind of system is often called an open loop system. There is no actual loop involved, but the term is so common I'm not going to fight it. It means that you use groundwater instead of a closed loop heat transfer fluid. This is a so-called doublet system. Water is pumped out of one well through the heat pump and then injected in another well. Flow can be reversed when switching from heating to cooling. A much simpler system, and this is the one we considered for our project, I call an open system. It just pumps water out of a well through the heat pump and then to a drain. This well can be the same well that is used for a potable water supply for a single-family residence. So the place that already has a private well already has a lot of the necessary infrastructure for geothermal heating. As of 2010, there were roughly 600,000 of these systems, closed loop and open loop. Most of the systems were closed loop, are closed loop, but a significant number of them are open systems. And with that, I will hand it off to Dave. Unless there's a question.
Oh, here it is up here. You always these interesting messages that show up all the time. Update. Come on. There we go. So I'm going to talk about the groundwater resource aspect of this thing and talk about two areas that were selected for this pilot project, if you want to call it that, American Bottoms and Mason County. The purpose was to look at the existing information that we have, both for groundwater availability and groundwater quality, in order to figure out where open loop systems are feasible. One of the things that is interesting for this is that heat content of groundwater is not typically looked at in terms of assessing groundwater as a source of supply. We went through an exercise in water resources planning for East Central Illinois and Northeast Illinois as part of the governor's initiative from several years ago, and a lot of issues that were discussed during this time. One of which was not the heat content of water, either groundwater or surface water. So this is something that's kind of new, and it needs to be better integrated into those kinds of exercises. So what kind of data am I talking about? There's geologic data, what kind of stuff is there in the subsurface, hydrogeologic data, hydraulic data, water levels and such. There's data associated with groundwater quality, but specifically as it relates to heat exchange performance and efficiency, and then also groundwater use. And the idea was to bring these things together. Okay, Xinli. Bring these data together and serve it on something called something similar to IllWater. IllWater is a web-based server that the ISGS has, so I'll do a little sidebar here. We serve up water well data that we have in our electronic database through something called IllWater, and you can find it on our homepage if you're not familiar with this and are interested in it. Near the top of our homepage, there's something called IllWater, one of the tabs, and so if you click on that, it brings up another window that has instructions on how to use IllWater. It explains the symbols. It explains what the data are. So if you click where I indicate there, it opens up another window that includes all of the state of Illinois, and also kind of gives you a little map to kind of show you where you are. The levels of information are appropriate to the scale of the maps. You can't see things that are inappropriate for the scale at which you are. On the left-hand side, there's a number of tools that can be used to manipulate the map and acquire the data. So, for example, if we zoom in to the western edge of Mason County, which is this county right here, we see that all of a sudden the sections show up, the numbers show up. There are dots there that represent the location of water wells for which there are records in the ISGS database. So if we select one of those, say this one right over here, what appears then in another window is a facsimile of the water well record that was filed by the driller. So it gives information on location, who drilled the well and for whom. It gives the well construction information, and it also gives the materials that the driller encountered when he drilled the borehole to install that well. And these are his descriptions right here. These are not a geologist's descriptions or anything else like that. There are engineering borings and some other borings in the database, and the terms that are used to describe the materials are as appropriate. So two areas were selected from the hydrogeological perspective. There were two criteria. One was a prolific aquifer, and this map from the Water Survey indicates estimated potential yield of sand and gravel aquifers in the state. The yellow represents a yield, estimated yield, as you can see, from 200 to 300,000 gallons per day per square mile, and the orange is a little more, 300 to 400,000 gallons per day per square mile, and also for which there was an abundant amount of information. So the first area, or one of the areas, is Mason County, located here. This represents a rural setting, and so the geothermal applications would be more appropriate for agricultural uses. The second area is the American Bottoms down in Madison and St. Clair Counties. This is in an urban area. It was heavily industrialized at one time. That it's being de-industrialized now. And so those applications, geothermal applications, would be more for commercial or industrial uses. There are some groundwater quality problems that I won't go into because we have a geochemist here. Now, American Bottoms, if you're not familiar with it, East St. Louis, it's a floodplain. The western boundary is the Mississippi River. We're only talking about Illinois here, so we can forget about Missouri. The eastern boundary is a bluff right along about in here that is formed by a bedrock high plus the glacial deposits that overlie that bluff. The width is from 2 to 9 miles, 9 miles at its widest, and the length is about 30 miles north to south. The bedrock that underlies the American Bottoms is kind of a flat terrace feature. It's steep, the bedrock surface is steep along the bluffs, elevation about 360 to 400. It falls off rapidly from the bluff towards the floodplain, towards the river, to about 320, and then it's a fairly gentle topography across the rest of the American Bottoms. There is a channel that was incised into this bedrock surface. The importance of the bedrock surface I'll come to in a minute. The thickness of the materials, the sediments underlying the floodplain, you can see that they are thinnest along the bluff. The maximum thickness is up in this area here. It's 171 feet. Commonly, it's 100 to 120 feet. Saturated thickness depends on the level of the potentiometric surface, which is either a water table or in the areas that are semi-confined, it's a potentiometric surface. Why is the American Bottoms an important area, and why is that aquifer there? As you may know, the upper part of this country was glaciated several times. This shows the glacial extent of what we call the Illinois episode. This is about 125,000 to 180,000 years ago. And then the Wisconsin, which is the last glacial episode, the yellow indicates sand and gravel that was deposited by meltwater flowing from the glaciers. And these are not just little streams. These would put the Mississippi River to shame at a peak flood. These are enormous amounts of water that are coming down here, but you see where the focal point is, right here at the American bottoms. And so we have all of this meltwater coming down here, depositing sand and gravel, and a cross-section of the American bottoms shows that there's sand and gravel down at the lower level, sand above that as that meltwater volume was reduced. The sand was carried further down, the coarser material was left further to the north, and this was followed by fine-grained sediment, silt and clay, that's typical of floodplain deposits. So the aquifer in the American bottoms is very productive. One way we can indicate productivity is by transmissivity, which is gallons per day per foot of material. So you can see it ranges from about 50,000 near the bluff to as much as 300,000. Groundwater use in the American bottoms started around 1890s when industrialization started to take off. It increased until it peaked at about 1956 at a little over 110 million gallons per day. Things changed, the use of the land changed, deindustrialization occurred, and groundwater use kind of fell off. The latest part of this graph is 1990, and it's about 60 million gallons per day. Most of that water pumped was for industrial use, but some of it was for public water supply. So what do we have here? This reduction in pumping has resulted in that potentiometric surface, or the water table, to start to rise. In the meantime, what had happened is that roads have been built and other infrastructure had been put in place under those conditions where the water table was lower. Now all of a sudden we have roads that are being flooded because of this water table increase. And so IDOT has gone in and installed some dewatering sites to keep the interstate dry, since we all don't drive AMFA cars or something like that, and they're pumping about 15 million gallons a day. So the idea is, can we use this water for some geothermal application, because we do have a significant amount of water being pumped and it has a certain energy content. Now the second area, the rural area, is Mason County. It's, like Tom said, located smack dab in the middle of Illinois. It's on the western end of the Mahomet Aquifer, which is an aquifer that extends across the central part of Illinois to the state line over here. Mason County has a lot of sand and gravel, as you may know. The sand here is indicated in yellow, sand and gravel is in orange. Just a little blow up of that map. The sand and gravel forms what they call a sand plain in most of Mason County. It has a rolling topography because there's sand dunes down there, and that's called the Havana lowlands. In this area here, it's pretty much sand and gravel from land surface down to bedrock. There's an upland in southeast Mason County that has a bedrock high, and over top of that is some glacial till, which does have some sand and gravel that has groundwater in it. Now this area here was deposited by the glaciation during the Illinois episode, and you can see that's about 125 to 180,000 years ago. The bedrock surface in Mason County consists of a large valley called the Mahomet Bedrock Valley, and this valley extends just like the Mahomet Aquifer to the east to the state line. There's some other valleys too. We have a bedrock valley that comes in from the north, and this was the course of the ancestral Mississippi River. The Mahomet Bedrock Valley is part of a larger drainage system that was pre-glacial in age that extended into Indiana and possibly into Ohio and maybe down into West Virginia. So the sediments overlying the bedrock are thinnest along the western edge of Mason County on the Illinois River, where they're about 25 to 50 feet thick, and they the maximum thickness is along in this bedrock or this upland in southeastern Mason County, where the thickness may be 300 to 400 feet, and then there's some sand dunes that provide some thickness of the quaternary sediments. The way we calculate that is just take land surface and subtract bedrock. elevation from that. So we have a saturated thickness, which is everything that's below the water table or the potentiometric surface. And again, it's thinnest over here on the western side along the Illinois River. Maximum thickness occurs right around in here, about 180 to 200 feet thick. What does this mean for groundwater availability and groundwater use? This is just a map from a recent water survey publication that shows the location of high-capacity irrigation wells. And then the red dots are high-capacity municipal wells. So there's a lot of use down in Mason County. So my summary is that there are opportunities for geothermal applications. Both are underlain by very productive aquifers. One of the things about that is that the well and the equipment for pumping groundwater is present, and that's generally most of the cost for developing such a system as an open-loop geothermal system. Now, these costs are there because of other, they've been paid for other reasons. The well is being used to supply water, either for industry or for a home or something like that. So these wells exist. And the other thing is that there are unused or maybe abandoned wells that are present in the area, that it wouldn't take much to retrofit those for the same application. So what are the advantages? There's a potential to reduce development costs, to minimize pricing, to reduce power consumption, and also any kind of temperature loss that comes from transferring water from the well into where the heat pump is located. Another advantage is that it may help solve some of these flooding problems. I mentioned, and you may have heard in the news, Havana has flooding problems off and on. And what happens there is that the water table rises until it intersects land surface, and then it becomes surface water. And so they really don't know how to take care of that because it would take a lot of dewatering wells like in the American bottom. So using the water for geothermal applications may help solve some of those problems. So thank you for my presentation. In case you don't know, here's a high capacity well. This is what they look like. And here's a domestic well. Any questions while we're getting ready? Oh, good. Xinli?
Okay, my part is to estimate the heating and cooling potentials of this in this project. So to do that, we actually considered we actually carried out the following aspects. In this talk, I'm going to cover mainly these four aspects. The first one is the model, the ground water source heat pump model we used in this study, and the second one is the weather data that we used for this research, and the third one is heating and cooling requirements for each single typical single-family houses. The two models we used here, and the last one is based on those data and the model, we estimate the heating and cooling potentials of the two studied area, as David mentioned before. This diagram shows the ground water source heat pump model, which is a typical engineering flow diagram, which we usually call this is the principal flow diagram. On the left side, this is the heating mode. Right side is cooling mode. So generally, heat pump is actually a device which can move the heat from one part to the other. Why we call it heat pump is that we can move the heat from the low temperature region to the high temperature region. And to do that, we need to do the work. We need to input electricity in the heat pump system. And in this case, in the heating mode, we actually suck the heat from the groundwater and transfer that to the house or buildings. And generally speaking, the coefficient of performance of a heat pump system is definitely greater than 1. Usually it is about 3. So that means if the COP is 3, if we put 1 part of electricity, we can suck 2 parts of the heat from the groundwater, and then we can supply 3 parts energy to the house or building. So this part is for the cooling mode is actually reverse cycle of the heating mode. We actually suck the heat from the high temperature room during summertime, and we dump the heat to the groundwater. That is a very typical flow diagram. For the energy balance for heating mode, we usually have 5 governing equations. We have no time to describe that in detail, but we can see that we have COP here, and I'm going to talk about that later. And this is the cooling mode. We also have 5 equations, governing equations there. The definition of COP in heating mode is that heating capacity over the electric power input. And in cooling mode, it is cooling capacity over the electric power input. But in the reality, in the utilization of heat pump system, based on the current available ground source heat pump system, we use the COP. In this study, we use the COP in the range between 3 and 4 for our calculations. And for the cooling mode, we use COP it's between 3.5 to 6.7. In America, people usually use the EER, which is energy efficiency efficient ratio. In this case, it has the unit. Unit is BTU over every hour and every watts of the input electricity. The groundwater temperature we use is based on the data set from the Illinois water survey. So for both heating and cooling case, we used 15 degrees centigrade. And for the return temperature, it is different. For heating mode, we use 10 degrees centigrade, which is the groundwater minus 5 degrees C, which is based on the engineering design code. So generally, we design we let the temperature drop in the groundwater heat exchanger as about 5 degrees centigrade. And in the cooling mode, it is we use 26 degrees, which is the building return temperature, which we set as 24 degrees centigrade, plus 2 degrees, which is the heat exchanger approach. The weather data of Mason County used is from the ISWS website, which is for the 3-decade climate normals. So HDD here is the heat degree days, and the CDD is the cooling degree days. So this is the average data for each month. And this is for the American bottom, which is from the same data set. For the heating requirements of a typical single-family house, we used 2 models for the calculation. The first model is the Lawrence-Berkeley model, and the second one is the multi-page model, which is actually a spreadsheet calculator. And in both models, we did the heating. We calculated the heating load first, which is of the building, which is monthly heating load, and then based on that, at Shell, we can find out the monthly average mass flow rate of the groundwater. So that is actually the pumping rate for each single house that is needed. We compared the result between the two models, and this is for the Madison County. And for each case, we considered a one-story house, two-story house, and we can see that this is the variation of the average well production rate, which is a well pumping rate. And this is from January to December. So if we move forward, we can see that this one is for the American bottom. It has the same shape. And for both cases, we can see that the two models have a very good agreement. So in the following calculations, we only use the Murray model and to do the sensitivity analysis. And in the sensitivity analysis, we estimated the monthly average well production, which David usually calls its well pumping rate for each single family house. And we choose the different COP values for each calculation. And for heating mode, we use the COP equals 2, 3, and 4. And for the cooling mode, we used 3, 5, and 7. This diagram shows the sensitivity analysis of the two-story single-family building, which we can see this is the COP, different COP. This vertical is still the ground. Is still the average well production rate, which is the pumping rate in gallons per minute. And you can see that the heating is 0 during summertime. And the highest heating rate is in January. It's about 2 pounds, 2.8 something like that. And there is a similar trend for the American bottom heating here. You can see that the highest still occurs in January. It's about 2.5 gallons per minute. And for the cooling mode, it is different. There is no cooling, definitely, but only in the summertime. You can see that, which is between May and October. And the highest pumping rate is about 3.5, and in the American bottom, the pumping rate, highest pumping rate is about the same. We then estimate the heat and the cooling potentials of the two studied areas. The two areas, as David mentioned, is the Madison County and the American bottoms. In the American bottoms, we only consider these two counties because of the documented pumping rate that I can use. The method that I did this calculation is based on the following procedure. Given the highest monthly pumping rate for each house that I showed you before on the previous 4 diagram, we choose the highest one. Highest pumping rate of 3.5 gallons per minute, and we, based on the documented pumping rate at each sub-area, we can find out the total number of the houses that the heat pump can supply. This is an example that David gave me in our report. You can see that this is in Madison County. We actually completed 2 studied areas. And those dots indicate the location of the production wells, and the number beside that is represents the pumping rate in gallons per minute. Based on those models and the data, and also the total pumping rate in each studied area, we find that the numbers of the houses at each area. In the American bottoms is nearly 7,000 houses, single family 2-story houses that they groundwater source heat pump can supply. And in Madison County, it is about 3,000 houses. And this then gives us the those data here. We can calculate the groundwater heating and cooling potentials based on the number of houses. And in Madison County, it is about 4.5 times 10 to the power of 11, which is in kilojoule per year. And in American Bottom, it's about 12. It's about 10 to the power of 12 kilojoules per year. And the total is 1.4 times 10 to 12 kilojoules per year. What does this mean? So I compared this with this figure without the UI you see about power plants, our power plant here. The power plant has the nameplate, that is the total installed capacity, as 47 megawatt steam turbine installation. And if that total capacity steam turbine running for 1 year continuously, and which can generate 4 times 10 to the 8 kilowatt hour. So that's about that. But generally, in reality, the power plant cannot run that 24/7. So I checked the data online, and it shows in 2005, the power generation of the power plant, about power plant, only generate this much of electricity. And that means this much of energy, it costs about 19 times that the electricity generated in 2005. And that give us a general idea and how big that energy that we can use from the groundwater. So we can see that the groundwater has a great heating and cooling potentials from this calculation, and it's really a good source for the heat pump applications. So if you've got any questions, or you can ask me later after Tom's presentation. Yeah.
Could you do the numerical comparison again between the thermal energy in the groundwater and the average plant? Wasn't one in kilojoules and the other in joules?
In kilojoules.
For both of those? You could flip back a couple.
You mean this one? That is, you mean here?
Okay, these in kilojoules.
Yeah, they're all in kilojoules.
What's the difference between the LBL model and the moon phase model?
Yeah, the moon-phase model is actually a more general model. As I mentioned, they give you the first autocorrect calculation result. And why we use the Lawrence-Berkeley model is that we just want to say how accurate the first order that the online calculator mentioned. So the Lawrence-Berkeley model is more specific. They actually set up the prototype models of 4 different houses and did the measurement and did the correlations. So we use that to check the second model.
So can you go to the slide?
Which one?
Yeah, well, it compares the LBL.
Okay. Yeah.
So the moon phase model always possibly biased with respect.
It's no. You can see that actually the LBL model is the bottom line and the top line. So the Murray-Page model is between. So yeah, that gives us a very good chance to compare that and make a decision. Yeah. Yeah.
I'm looking to get here more of a big picture view of the comparison, which is to say, we can extract a lot of thermal energy by putting electricity into the heat pump, right? And so one comparison is we put electricity into an air source heat pump. but I anticipate the answer is that the average coefficient of performance is lower because of the outdoor temperature variation. So here instead, we say we put electricity into
Groundwater.
Groundwater.
Yeah.
The coefficient of performance is higher. We're also putting electricity into pumping water, right? So now we have two electrical inputs to get the heat out. But perhaps the argument here is essentially a co-productivity argument. You would be pumping the water anyway in the bottoms, or you might say you're pumping the water anyway because it's my drinking water or something else. But you see what I'm saying?
Yeah. Yeah.
If we do the total numbers, we have a big, the bottoms, for example, you have 2.5 megawatts of thermal energy for each degree C to change that water temperature. I worked out the numbers while you're talking. So that's not small, but it's not huge. Right? I'm trying to see the big picture of all the inputs and all the outputs. Wondering how does that look from your perspective?
We didn't consider things in that detail. We didn't go that far. But what we're trying to figure out is that we want to consider everything into the COP. So if the COP can consider some of that. You mean the two pumping electricity, the two electricity that used for the pump. The pump, one is for the groundwater, another is for the heat pump. So we did not go that far, but that's a good point. I think that's I'm just wondering if we can consider that totally into the COP as the ground source water heat pump. I need to check that. This COP I got, the range is from the Canadian report. I think I can check that. Yeah.
And you would build it into the COP because you're not putting it into the water while pumping out. We haven't included that in our cost comparison, but it would not.
Yeah. But that's a good question. In the design, you really need to consider that. Yeah.
Well, you have two cases, right? I mean, in East St. Louis, you figure you've got to pump the water anyway, right? You're basically saying, I have this thermal energy loop that I'm pumping anyway, and I now extract heat out of it. The coefficient of performance is pretty favorable because of the starting temperature. That was pretty good. In other cases where you might not have pumped the water in the first place, I'm just interested in the energy addition because you're now adding pumping.
Yeah. In the design, we really need to consider that. But for this estimate of the heat cooling potentials, I think we just use the average COP supplied by those references. I think that's probably good enough for the first order. Yeah.
Well, in your source heat pump, you still have to pump air.
Yeah, that's another. So we need to do the comparison.
There's always a cloud.
Yeah.
Sure.
Yep.
Does it have any influence on the ground or on the ecosystem if you heat up the ground water about 2 degrees or cool it down?
You mean the ground temperature going to change?
Yeah. So if you change the ground temperature.
Oh, in this case, we didn't use the closed loop system, so we only consider the groundwater system, and based on the data from the water survey, we think that the change is very, very minor. So we just use the 15 degrees centigrade as the average groundwater.
It's going to be cycling too because you're very cool. You're dumping very cool, so you're going to get some of that back out.
Irrigation is seasonal, so how do you allow for that? And does pumping bottoms take place 12 months a year or certain months?
Dave, can you answer that question?
For the North Bob, well, irrigation is seasonal, yes. So the priority there would be to look at whatever domestic level
These wells are certainly available.
Oh yeah.
I have a question for the day.
Oh.
You have some managing the, you have enough on the water. I just wondering for some case like a dry season, but like for example, like last year, very dry, hot. I just wondering for groundwater enough for the heating or cooling last year at this areas.
Well, in a drought, there's water still being withdrawn. And so the idea here is to use the water that's being withdrawn and use the heat content, the heat energy in that that's already being pumped out for other reasons. And one of the things about groundwater management is taking into account the effects of drought and how much water is being pumped out. And there are other things that need to be done and issues that need to be addressed in times of drought. And on the other side of that coin, in times of water surplus, are there things that need to be considered in terms of overall groundwater resource management?
Yeah, you can.
I'm going to comment here. I think the bottom line is the water in the case they are using is going to be top up anyway, and they are not competing with water resources. Because that's the water they want to pump out to make sure water table independence on some level. So it's a resource. It's not really competing with drinking water or irrigation. It's the resource that is the water they're going to pump out. So, but still, I think here's my question here: is how important is the water quality? Although the water is going to be first speaker.
Yeah, third speaker is here. We're going to talk about that. So can I just give time to Tom? Yeah. Yeah, we can. Yeah.
And then please repeat any questions that you get.
Oh, sorry.
We're running a little overtime. I'll try to talk fast. Groundwater quality can affect heat pump operation through fouling, which is the depositing precipitates on heat exchanger surfaces. This is not a heat exchanger. It's a domestic hot water line. But it shows that calcium carbonate deposition can sometimes be a problem. And the other possible effect is corrosion. I won't have too much to say about corrosion, mostly about the fouling. Calcium carbonate is a very poor conductor of heat compared to stainless steel, which is what heat exchangers are made from, the ones that are used in domestic applications. This graph was originally done for boilers, the operation of boilers, but the principle is certainly applicable to heat exchangers too. Very thin film of calcium carbonate can have significant effect on heat exchange. This energy loss on the y-axis is reduction in heat exchange efficiency. So if you have a 2 millimeter film of calcium carbonate, so-called normal calcium carbonate, you're going to get a reduction of about 5% in heat transfer efficiency. This means you're going to have to put 5% more electrical energy, more or less, into your heat pump to get the same amount of heating or cooling. If the scale is high in iron or has iron and silica, then scale formation can be even more problematic. This graph shows silica and iron concentrations in Mason County and Madison County. One of our American Bottoms counties, St. Clair, is similar to Madison County. This is a box and whisker plot, which is a good way of summarizing lots of information. This is from our groundwater quality database, and these summarize hundreds of records in the database. For silica, American Bottoms is definitely higher in silica. The median concentration, which is the middle of these boxes, is higher than the 90th percentile for Mason County. So silica might be more of a problem in the American Bottoms, and iron is definitely higher in Madison County or American Bottoms than Mason County. So it looks like scale formed in the American Bottoms could be more of a hindrance than in Mason County. Scale formation depends on a lot of things. I'm going to spare you the details. The next slide, I'll just show you the results of my calculations. Depends on calcium, alkalinity, pH, temperature, ionic strength. And calcium carbonate is one of the few salts for which the solubility decreases. That is, the solubility product gets smaller as temperature increases. So since groundwater in almost all wells in Illinois is close to saturation with calcium carbonate, scale formation should only really be a problem when a heat pump is being used in the cooling mode. So here are the results of these calculations, letting the system reach equilibrium with a delta T of 10 degrees. That's pretty much what Xinli was using in his thermal calculations. There's a range of results because there were ranges in the water quality variables for both places. All the wells except one in Mason County precipitated some calcium carbonate. The median is about 18 milligrams per liter. Not much siderite or ferrous carbonate in Mason County. American Bottoms shouldn't be too surprising. From the higher iron concentrations, there was much more predicted siderite precipitation, and there was also a wider range of calcite in the American Bottom. So in both places, there's likely to be some scale formation. There may be the so-called high iron scale in the American Bottoms. I took that median precipitation amount from Mason County in the previous slide, and 4 gallons per minute. That's just slightly more than the maximum that Xinli predicted that you need for cooling. Made some other approximations, and I estimate that in a 5-month cooling season, you ought to get about 1 millimeter of calcium carbonate deposit. There'd be a significant loss, but not a serious loss in heat transfer efficiency. It would be a good idea, though, for heat pump owners to clean out either by themselves or have a contractor do it at the end of the cooling season before heating season really starts. I'm not going to say much about corrosion, just that I compared the values of this ratio, which came from a report by Larson and Skold. These were two chemists at the Water Survey. They studied corrosion of cast iron in Lake Michigan water. This report was from 1957. They calculated the ratio of sulfate plus chloride to bicarbonate. This is all in equivalents per liter. And found that for values of this ratio less than about 0.75, there was hardly any corrosion. About higher than about 1.3, that's when corrosion got really serious, and then there was intermediate effects for values in between. The American Bottoms has much higher sulfate and chloride concentrations. So this Larson-Skold ratio, the median value for the American Bottoms is higher than the 90th percentile for Mason County. So corrosion is likely to be more of a serious problem in the American Bottoms than Mason County. And just finish with a few other factoids about groundwater heat pumps. As I mentioned earlier, there were an estimated 600,000 systems in the U.S., which may seem like a big number, but that represents less than 0.5% of the number of single-family houses in the country. Retrofitting, 20% of the single-family houses in the country would have significant environmental benefits. The U.S. Department of Energy, in this report from 2010, estimated that primary energy use and CO2 emissions could be reduced by about 9% and summer peak electricity demand by about 11%. So that's nothing to sneer at. This is from another recent paper that reviewed heat pump use in 17 or 18 European countries. I just took the data from 4 of these countries, plotted on these 2 graphs. The one on the left, absolute savings in CO2 emissions in millions of tons. One of the things that is really striking is the apparent rise in the heat pump use from 2000 to 2008. The other is that Sweden seems to have really taken 2 ground source heat pumps. No other country comes close in the savings of CO2, either in absolute terms or in percentage terms. We have a large-scale groundwater heat pump system in operation not too far from us. The Muhammad IGA uses groundwater for all of their refrigeration. This slide came from a talk given by Lon Huber here at ISTC in 2010, and this is still available on the IST website if anybody would like to take a look at it. I recommend it. That was a very good talk. Dave already showed this. There's already the infrastructure in place for heating and cooling, both in Mason County. One of our colleagues, Doug Herman, sent us this picture of a refrigerated warehouse, and I don't remember, was this already using groundwater, or is it something that he said could be? Do you remember, Todd? Maybe it could, yeah. Certainly if a grocery store can run its refrigerators and freezers, a refrigerated warehouse could do the same. And as Dave mentioned, the American Bottoms is another place that already has a lot of this infrastructure in place. And okay, so now I'll open up to questions either on water quality, water chemistry, or just anything. That's the end of the talks. Yeah,
those cases you show in the end, are they all like a closed loop or open loop?
Like that's an open system.
All those, and then the one next to all open.
You mean like these?
The one next to the actually one goes to another.
These certainly would be open. You'd have to drill another well in order to inject it, and actually injection wells have their problems. I don't think it's a good idea. So this would be an open system.
So since the like water quality issue you mentioned, an open loop system, major open loop system, is it necessary to use groundwater? So for example, can you harvest this energy from the other source of water, for example, like power generator, or nuclear plant, or the wastewater treatment? Well, because those water has a different signature than the river or the lakes they are coming to. And usually those water are hotter than the river or lake water. So since you already have this system, can the system be all mixed right away?
I'd like to repeat your question, but I'm not quite sure.
Show question is, does your system have to use groundwater? Can it be replaced by the other kind of the water source? For example, power generators, clean water, or the wastewater treatment plant, the water from wastewater treatment.
Okay, the question is, besides groundwater, can other water flows like wastewater, can you harvest heat from those? And the answer, I think, is absolutely yes. Like the Champaign-Urbana Sanitary District certainly could extract heat from their effluent before putting it into the Finney Branch or Copper Slough before they send it out. They have such a large flow that there wouldn't have to be much of a delta T. If you really warmed up the water a lot, that could be a problem for the organisms living in the receiving stream. But if you're just using the heat just for the plant, you wouldn't have to heat or cool it too much. The same thing applies for potable water. I think you can extract heat or dump a little heat into the water. Illinois American wells, it wouldn't make a lot of difference if you changed the temperature by half a degree or something. But the flow is so large, you can get a lot of heat out of it. Did that answer your question? You first.
I think you presented the first few slides.
Yeah.
I noticed in some of the diagrams you had a heat exchanger in conjunction with heat pump. Is there a specific reason that that's preferable just running the heat pump?
I will let Xinli answer that. And Xinli, could you come up here to answer the question?
Yeah, which slide?
Can you come up here?
Your schematic. Just schematic. Oh, my.
Just repeating the question, is it necessary to have a heat exchanger and a heat pump?
So the question is that do we need this one heat exchanger here? Or? Yeah. That's a good question actually. So this is the you can have different designs. You can actually build in that into the heat pump as one equipment. Is that your question? Yeah. That is which is called built-in heat pump exchanger. So you can have a different one, which is the larger one outside that, but connected by another loop. So yeah. Yeah, it really depends on So the design depends on water quality and the easy of cleaning, and also the take off this skating things like that. So
the experience at the IGA store was that they needed to have that intermediate step, because if they allowed the groundwater to go right into the exchange without the intermediate step, they get started to follow the exchange. Mm-hmm. And then the store owner was finding that his costs were going up. And once they put that intermediate step in there, then those costs ramified over the price of the exchange. So that was either clean out or
yeah. And speaking of the heat exchanger types, and currently we are, I think commonly we use the plate heat exchanger, which has very high thermal efficiency, and it's also easier to clean the plates and easy to install that again back up.
It's similar to the AC system, right? So AC system using air cooling.
Yeah.
Right, but they're using water. So how much energy you can see comparing the normal regular AC system? You can see for like cooling, high temperature, how much electricity you can see using water.
Okay. The question is that how much energy you can save compared in comparison between the groundwater heat pump and groundwater source heat pump and the air source heat pump system. We did not do that yet, but in theory, if you're looking at the diagram that Tom presented at the very beginning, you can see that, and based on thermodynamics, that's very clear, because you can see the temperature difference there, and the groundwater is almost the same across the whole year. So yeah, but we did not do the technical economic analysis in detail.
Yeah, we didn't do any economic analysis, but there are comparisons available on the internet. Probably should have put a couple of these in the introductory remarks. Using groundwater for cooling instead of air has some big advantages. I'm sorry I don't have any numbers for you.
Is there any hydrogen sulfide?
Yeah, just from my own personal experience, I've sampled some groundwaters in Mason County. It does happen, and you're going to have corrosion issues, of course, if you have hydrogen sulfide. There are some groundwaters that probably shouldn't be used for this. Yeah, Todd.
What's the sensitivity to the temperature rise, the delta T temperature rise and precipitation? I mean, is it a linear thing, or is it? So what I'm thinking about is, I was impressed by the maybe 3 to 4 gallons per minute. And so I'm thinking, okay, well, if you that's not very much flow, so you can increase that flow and have a lower delta T. You have better COP, and then also maybe less scaling. And so I'm just kind of wondering that, I'm kind of wondering how might that factor into precipitation?
The question was, how sensitive is the amount of calcium carbonate precipitation to delta T. Is that a fair restatement of your question? It's nonlinear, but for small temperature changes, it's almost linear. If you do use a higher flow rate, therefore a lower delta T, then you will probably have less scaling because there will be less of a driving force, and also the water will be in the heat exchanger for a shorter time. One of the assumptions I made about the amount of scale building up had to do with kinetics. So I think both cutting down on delta T and cutting down on the residence time will reduce the scale formation.
Question about the final application. So, the point at which the water is pumped out, and then you have a sink of heat, which presumably is some kind of commercial building or residential building. And however is actually the source of the heat and the sink of heat, you require some kind of transmission distribution system. And so our existing wells that we're talking about suitably located so that in fact they can serve where the energy might actually be used, or is it for new applications?
The question, correct me if I get this wrong, is are existing wells close enough to the buildings that would be heated or cooled, like in Mason County? If you're on a farm and your irrigation well is a quarter of a mile away, is this going to, there going to be so much heat or gain or loss that it's going to be impractical? I don't think so. I think the line could be buried, so your exposure to air would be minimal, and the flow rate, I think, would be fast enough that you're not going to lose a significant amount of heat. I'm just guessing, but I think in Mason County, for an individual farm, that's not a problem at all. In the American bottoms, since the flows are so great, I think a pipeline could be built to a refrigerated warehouse. It doesn't have to be right next to the highway. You would have issues about going across private property. That could make or break the deal. Certainly, it's going to be a factor to be considered.
The discharge has to be then downstream of the place where you are pumping.
Yes. Yeah, it would be a storm sewer or something like that.
You may want to take it to the sink and then back or something like that.
The question was once the heat has been exchanged at a distant building, does it have to be piped back to where you got it? Is that correct?
Well, it has to be downstream someplace.
It has to be downstream someplace. It can go right to the drain by the building where the heat is being used. Of course, the drain has to have adequate capacity, and that could be a problem.
A comment on the issue of the heat pump and the heat exchanger. I know by experience, that it's more expensive to repair the heat pump or the system, close to the final target, and sometimes it's better to have the heat exchanger and then have a better quality of water upstairs. I have to say, I'm trying to go back and revamp the geothermal system program that one time that we had over here. and I'm looking for opportunities to try to connect the clients and suppliers of geothermal systems to see if we can have a more of that 45% that seems to be there. Because if anybody has any ideas or good vendors that may be able to assist us in that, please let me know. I'm Luis Rodriguez. And second, I thought Larson and I and Xinli are the ones that are going to be working on that. There's going to be working on it. And the other part is I want to say that I do not know about geothermal systems, but I do have a geothermal system in the house I built in Champaign. Those systems, even though it's not the same one as my closed loop system, but I am very satisfied with it in the 30 years. Which I still wonder why it's not being used more. Anybody that has any input or information, I would like to understand that too.
Boy, how do I summarize that? That's something I would like to know too. Why geothermal systems aren't more popular. They certainly have their advantages. You couldn't, in most of Champaign and Urbana, you couldn't use an open system. There just isn't the groundwater available. Is that a fair thing to say? Yeah. In northwest Champaign, up by Parkland College, that's the edge of the Muhammad Aquifer up there. You could find enough groundwater, but in most of Champaign-Urbana, you'd have to use a closed-loop system.
I think the cost time of return is long. So the time that you make up for the cost that you paid initially is longer
than that's true. I actually, before I cut my introductory talk down, I did have a slide on that. The so-called payback time, geothermal systems are more expensive to install. If you remember, one of the first slides showed the horizontal loop. That system obviously had to have the whole yard dug up, put the loop in, put the soil back in. Payback times depend on the kind of on what you use for your heat. Payback times are like 5 to 10 years. They're shorter if you heat with electricity, longer if you heat with natural gas, which is pretty cheap. Thank you for pointing that out.
One other comment on the ground source system. There are two modes of operation. If you're taking heat out and putting back a similar quantity of heat with the reservoir. However, if it's not balanced, for example, if you're taking out more heat than you put back, the heat's really coming to the surface down. And you can run a calculation for how much surface area you need average over here to supply the heat to that house. So it turns out when housing is dilute, when the yards are fairly large compared to the houses, you have enough heat flow from the surface down to make it up. But as the density changes, you reach a point where it only works if you're really borrowing heat from your neighbor's yard. Now this is spelled out in David McKay's book also. Okay, so in one case it's just storage, but in the other case it's really surface heat. Right, so that's another issue. We can't all do it in modern day.
Yes, I'm going down the expense in mine, and I don't know if the feet down, I'm not to the side.
Yeah, so if you're dumping heat in there, the air conditioning, then pulling it back out, hopefully in a quantum balance. It works.
We'll stop with any questions now, and anyone else with a question can come up and talk to our speakers. I'd like to thank Tom, Dave, and Xinli for your talk today.